Hello, this is my presentation in Deep Learning for Acoustic Signal Processing. This video will present my course project, which is split into two parts and is about the use of classification and different architectures within classification. So, as mentioned previously, the project is split into two parts, and the first part consists of the use of a long short-term memory, or LSTM, based emotional classifier to classify the emotions of a speaker. The Toronto Emotional Speech Set was used for this, which has 2,000 files of two female speakers saying a set of words with different emotions. And the LSTM architecture is an improved version of recurring neural networks, which are very good at modeling temporal differences in data, that is, differences in time. And that is perfect for modeling different emotions, as different emotions have variations in pitch and volume that other emotions may not have. And for this approach, Mel frequency capsular coefficients, or MFCCs, are very useful. They are taken from spectrograms, and since they are extracted over time, they naturally form a sequence of feature vectors, which makes recurrent architectures such as RNNs a very good fit. And when evaluating the model of the test data, it performed very well. As you can see in the confusion matrix, there is a strong diagonal dominance. It had an accuracy of 98.5% using an 80-20 train plus split. And the accuracy and loss of both the training and validation show that the model does not overfit to the training data, which is a very good sign. And the second part of the project focuses on the classification on spoken digits and environmental sound using a convolutional neural network, or CNN. The purpose of the project is to see how the CNN performs in these settings and which is better. And again, spectrograms are used very heavily on this. And for the spoken digits task, the Google Speech Commands dataset was used, which contains thousands of short audio clips of isolated words, including the digits 1 through 9, which was the ones used in this project. Each clip was converted into a Mel spectrogram, which captures the frequency content over time. And that transforms the audio into a 2D image-like format, which makes CNNs a very good choice due to their ability to recognize spatial patterns, and that is differences in space. And the model achieved an accuracy of 82.78%, which is very good. Most of the misclassifications occurred between the digits with similar phonetic structures, such as 8 and 6, or 2 and 3. And you can see in the confusion matrix on the left that there is a very strong diagonal dominance as well, which is good. For the environmental sounds task, the ESC50 dataset was used, and that contains 5-second clips of urban noises such as sirens, helicopters, and engines across 10 classes. And the sounds were split into categorical classes such as animals, domestic noises, urban noises, and so on, as well as a class consisting of random noises from each class. So each class was tested independently, and then we have the random class in the end. And as well as in the previous one, these sounds were also converted into Mel spectrograms for the CNN to have as an input. However, this dataset proved much more challenging, and while the model achieved nearly perfect accuracy on the training data, the validation performance was significantly lower, with the best accuracy as just 60% for some classes and as low as 48% for some classes. As you can see in the confusion matrix on the right, there is a much less diagonal dominance and much more misclassification. And this is probably due to the unpredictable nature of environmental sounds and their tendency to overlap or mask each other, especially in urban noise. There was a lot of overfitting. It was evident with the model memorizing the trained data rather than generalizing to the new and more noisy samples. And even though the model did not perform as well, I think that I showed how CNNs can perform very well and very badly. So they have a tendency to perform better when there's less noise, which makes sense, as there is as noisy spectrograms tend to be a lot more harder to discern from each other. So that was it. thank you so much. Thank you for having this course. I really enjoyed it, and it has been a very good experience to study in Spain. Thank you.